And practice quiz problem, we'll start with number 6. Find the horizontal asymptotes, or asymptote of this function. Okay, 30 seconds more. So the horizontal asymptote there is none. How come there's no horizontal asymptote? Because remember the question that we ask for horizontal asymptote. As the input gets super huge, what happens to the output? Well, these things become insignificant. These become insignificant. When x is really large, these two things dominate the numerator and denominator. And the number on the top is going to get way bigger than the number on the bottom because it's got a higher exponent on the x. When x is 1,000,000, that's 1,000,000 times 1,000,000 more than that one down there. And so any kind of ceiling you'd want to put as the height, it's going to crash right through. No horizontal asymptote. If the numerator has higher degree than the denominator, there's no horizontal asymptote. Do the next one. "30 seconds more. The horizontal asymptote on this one, well, if you FOILed out the denominator, it has degree 2. So the denominator has higher degree. So when x is 1,000,000, the bottom will be more than 1,000,000 times as big as the top. So when the denominator keeps getting larger and larger, it forces the fraction closer and closer to 0. And do part C. Find the horizontal asymptotes. Part C. "20 seconds more. Alright, the horizontal asymptote. This is the only case where you can get a non-zero horizontal asymptote. When x is super large, these become insignificant. These x to the 4th divide out, they cancel out. 8 divided by 2 is 4. This fraction gets closer and closer to 4 as x goes to infinity. The degrees are the same, then it's the ratio of the leading coefficients. Alright, give me a little feedback on number 6, parts A, B, and C. Okay, it's good to see that it's helpful for some. Alright, Discord should look a little different to you now. I had somebody very experienced in Discord help me set up so you're all color-coded. You should only see your group, and I can look real quickly and see how many are in each group and so on. And oh, in Discord there is Sulia Child. Who is this? Didn't know what group to put you in, because your nickname isn't your name. Celia Child, not here? Okay. Alright, let's go number 7. Putting it together, more parts. Find the x and y intercepts and the horizontal and vertical asymptotes. Okay, 30 seconds more. Alright, so x intercept. Set the y equal to 0. So you get 0 equals 1 over x minus 2. The only way a fraction can be 0 if the top is 0. But the top is stuck at 1. This has no solution. Thus, there are no x-intercepts. For the y-intercept, we set the x equal to 0. So then y is equal to 1 over negative 2 or negative 1/2. So this is the point 0, negative 1/2. And horizontal asymptote. As x gets super large, what happens to y? Well, the denominator is higher degree than the numerator. It's going to get closer and closer to y equals 0. For the vertical asymptote, what is the value of the input that causes the denominator to become 0? If x is equal to 2, the denominator becomes 0. So that's a restricted value, and as you get infinitely close to 2, the fraction gets really, really huge, either positive or negative. So that's all of these things, and we'd use all that information to help us make a better graph, or to analyze where the difficulties are going to come up when we see the graph, make sense of a computer image of the graph. Okay, a little feedback on A. Okay. Also, the way I have this set up, so I can see who's here in each group, I don't need you to report attendance anymore. I still need you, the group leaders, at the beginning of class, get into your group chat and state who is the spokesman for the day, each day. And also, there were some people who had multiple logins, and that can happen when like you get in with one device and then you get in with another device, or some other time it just, you wind up creating a new account when you didn't even realize it. So the extra accounts might be like Mushi's got 2, Monica's got 2. Anybody else notice that they have 2? Sasha? Yes, Sasha, you seem to be using this one up here, so this other one, I am going to kick you out of this other one. Alright, and alright, well, let's go back to, do this again. The instructions are the same thing again. Get the x and y intercepts, horizontal and vertical asymptotes. Okay, 30 seconds more. Alright, so x-intercept, set the y to be 0. Now 0 is equal to 3x squared plus 2x over 9x squared minus 9. Now when you set the denominator to be 0, that will give you the vertical asymptotes. When a fraction that's going to be 0 will only become really 0 if the numerator is 0. So this part we could multiply both sides by 9x squared minus 9, and then that just goes away. Or we can just realize that this only happens when the top of a fraction is 0. Now I'm going to factor out. It's a quadratic equation. So the two answers are going to be x equals 0 and 3x plus 2 is equal to 0. Subtract 2, divide by 3. Alright, so the x-intercepts are when x is 0, the y will be 0. And when x is negative 2/3, the y will be 0. Let's go to the y-intercept. You set x equal to 0, and then when you set x equal to 0, you're going to get y equals, you get 0 on the top and negative 9 on the bottom, which is just 0. So the y-intercept and the x-intercept, they share a point there, they're both at the origin. And then the horizontal asymptote. It's always y equals. As x gets super large, what happens to this fraction? Well, these back numbers become insignificantly small. These have the same power. They reduce out, you get to 1/3. The vertical asymptote. You set your denominator to 0. Factor that. You can tell that x -1 would cause this to be a true equation, and x +1. So -1 causes, oops, I was in wrong thinking mode. The vertical asymptotes are x equals -1 and x equals +1. All right. Give me a little feedback on B. Okay. Nice to get a variety of feedback here. Y 0, 0. When you substitute 0 for the x, the whole numerator zeroes out. So that makes the y 0. And vice versa, if you set the y to be 0, and then you solve it, you have to, you're then figuring out what causes the numerator to be 0, and one of those answers is x equals 0. Brianna, does that address your question, or do you have a different question?
Yes.
Okay. All right. Any other questions? Anything from homework?
I have a question.
Yes.
So when we're doing the y-intercept,
Yes.
and there's that's where I get a little confused when we have like the top and the bottom. Cause so we like when we have that kind of like B example, do we only do the top one? Do we only find like the x of the top one and not the bottom one?
Okay. Let me take a simpler example to show you. All right. So let me change color here. If f of x is equal to x minus 2 over x minus 5. And I say find the x-intercept. Okay, now how do I find the x-intercept? You set the opposite letter y equal to 0. And then you get this equation, 0 equals x minus 2 over x minus 5. Now, if x is equal to 2, this fraction becomes, f of 2 is 2 minus 2 over 2 minus 5, which is 0 over negative 3, which is 0. If x is equal to 5, f of 5 is 5 minus 2 over 5 minus 5, 3 over 0 undefined. This, at first you might think the solution to this is two answers, x equals 2 and x equals 5. But x equals 2 does cause this fraction to become 0. X equals 5 does not cause this fraction to become 0. It causes the fraction to be undefined. So that is not a solution. If it's one fraction equals 0, a fraction can be 0 only if the top is 0, not if the bottom is 0. Does that answer your question?
Oh, okay. So when we do the y-intercept and it's a fraction, that's why we only do the top one, because it can be equal to 0, and in the bottom one, all of them would be undefined.
That's right.
Oh,
Good.
okay. I think I get it now, because I was a little confused when I was doing the homework.
Okay. All right. Good question. Any other questions?
Hi, Mr. Shankin. This is Brianna.
Hi.
I had a hard time with the stretch when graphing with the homework.
What problem was that?
It's for number 51, how to write the equation.
This is 5.6?
Yes.
I don't see anything about the stretch. Let me go to here.
Like, so there's problem 51, 54, 57, 60, and 75 are all about finding the equation of the graph.
Oh, okay. All right. So we'll find the equation of the graph. So let's. The word stretch threw me off, but I think I get the general idea here. Write an equation and 54. All right. Well, I need to write a function that has a vertical asymptote at x equals -3. That means when I put -3, it'll cause the denominator to become 0, because that's what it means. The question that we ask for a vertical asymptote, what input causes the denominator to become 0? And then x equals 6 must have been x minus 6, so that x equals 6 also causes the denominator to become 0. Okay? Then it has x-intercepts at -2, 0. Now, what this means is when you put -2 in for the x, it'll cause the y to be 0. Now I could put minus -2, or I could just put +2. So when I substitute -2 in for the x, this becomes 0. 0 times anything will be 0. 0 on the top of a fraction makes the whole thing 0. Another one is when x is 1, it causes the f of x to become 0. And it will have a horizontal asymptote at y equals -2. Now, the degree of the numerator, if I FOILed this out, its highest power will be x to the second, so it's a second degree polynomial. Same thing with this one. So then the ratio of the leading coefficients has to be -2. So if I put the negative 2 up in the numerator, then if I FOILed this out, the first term would be negative 2x squared. The first term here would be positive 1x squared. The ratio of the leading coefficients would be negative 2. Okay, Brianna, does that answer your question?
Yes, that was helpful. I had it said stretch on the problems before, so that's why I was saying that, but it's actually the y where you put the negative 2 is where I was confused.
Oh, okay, gotcha. All right. Any other questions? I can see why this one would be confusing. We hadn't really done anything quite like that. It's kind of working backwards. Yes.
77?
Which one?
77?
77. Okay.
Yeah, 77.
77. All right. And we had not done any like this one. So let me capture this. Now, this one is going to be, let's notice if we factor out the numerator. X times x, give me the x squared. And then these two back numbers have to multiply together to be a negative. So the only way that can happen is if one's positive and one's negative. And then I need two numbers that multiply to be 6. But when I subtract them, I get positive 1 for the middle term. So I want 3 and 2, and I want the larger one positive. Alright, so this replaces this. Further, notice this. This and this is identical. F of x reduces down to x plus 3. Except if x is equal to 2, f is undefined. If x is equal to 2, you'd get 0 on the top and 0 on the bottom. 0 divided by 0 is also undefined. When you divide by 0, it's undefined no matter what. 0 divided by 0, on one hand, you'd think it might be 1 because anything divided by itself should be 1. On the other hand, 0 divided by anything should be 0. And then on the third situation, when the denominator is 0, you're supposed to have a vertical asymptote. And it can't make up its mind about anything. 0 divided by 0 is undefined. So the whole, when x equals 2, we have, oops, what's called a whole discontinuity. So if you graph this function, you would see its graph looks just like this. Y-intercept of 3, slope of 1, looks like this, except it's got a hole, right? Whoops, not there. Where is its whole? It's when x is 2. Right up here is where the hole is. On this graph. If this one appears, so normally speaking, remember we asked the question, what is the value of x that causes the denominator to be 0? That will normally be a vertical asymptote, except if that would cancel out. And then you would get what's called a hole discontinuity. And that whole idea, if it seems a little complicated, let me show you with a simpler example. F of x is x over x. Now, when x, look at this. When x is 1, 2, 3, when x is 1, you get 1 over 1. When x is 2, you get 2 over 2. When x is 3, you get 3 over 3. You always get 1. But when x is 0, this is undefined. This one is the same as f of x equal 1, what happens when you reduce this fraction, except at the whole discontinuity, which is when x is 0. Alright, so this was just a minor point. I'm not going to test you on this. This won't be on a test. We just wanted you to point out that there is an exception to that rule of the x that causes the denominator to be 0. Generally speaking, that causes a vertical asymptote, but almost all rules have some exceptions, and this is one of those for that. Good question. Anything else?
60?
60. Okay, write the equation of that one. And let's go here. All right, so we need to write the equation of this. F of x, well, I know it's got a vertical asymptote. What's this one, at negative 3? That means x plus 3. Negative 3's got to make the denominator be 0. Now I could have written that as x minus a negative 3. But that would reduce to this, because it could be always x minus whatever that intercept is. And then 4 would also cause the denominator to be 0. So those are two key features we need to have for this. Okay. And then, does this look like it has any, this has a y-intercept of 1. No x-intercepts. Doesn't look like it. It's the x-axis at all. Okay. So, y-intercept of 1. How do you find the y-intercept? You set x equal to 0. If you set the x equal to 0, you would get f of 0 right now, you'd get 3 and negative 4 like this. So I'm betting there's now that's going to multiply to be negative 12. We want to get 1 here, so I'm betting there's negative 12 times it up in the top so that this reduces to 1. And then if I put any x's in here, I would be getting x-intercepts. Like suppose I put x minus 5. Then when x is 5, it would be 0, and so we'd have an x-intercept right here. But we don't have any x-intercepts, so...
Wouldn't the x-intercept be 2? Or is that...
Oh, you're right. There's a one there. There's an x-intercept at 2. Thank you. I totally overlooked that. X minus 2 causes that to become 0. All right. And then, now we see that the higher degree is in the denominator, and that causes a horizontal asymptote of y equals 0, which is true. Yes. Appears to be horizontal asymptotes. These blue curves seem to get closer and closer without touching the x-axis. So this looks like my function. All right. Any last questions? Those are all excellent questions, and let's do this. Let's start on this new section, and then we'll take a break in just a little bit. The next section is called 5.7 Inverses and Radical Functions. And before we start out, I have a couple things I want you to do. Come to Discord, the main chat, and so this OneNote, type yes into the main chat in Discord if you've downloaded OneNote and you're using it so that you can look at the notes at any time. And let me just kind of get a feel if there's folks who are doing that. Anybody? Getting OneNote, downloading it, can look at it anytime. The instructions for that are in the very first announcement. And you can also be having OneNote up. It's not reliable for Elliot. Anybody else having that problem where it's not being reliable? Okay. I haven't heard of that in the past. But you could get into OneNote while class is going on. It'll be a little bit behind. Like, you know, when I write something in, it might take 30 seconds, might take a minute or so for it to show up on your screen. Okay. All right. The other thing is, all right, this inverses and radical functions. If there's a number of you who had me as your instructor in college algebra, we are going to be doing, we had the topic inverses, and I'm going to use a lot of the same material. And this will be a really nice opportunity for you to go deeper into the material than what we did before. It's one of the issues in math is we often at the college level are going so fast that the depth is hard to get the big depth in. And so you're going to have an opportunity to go deeper into this. And we're going to use a lot of the same activities that I used last semester when we covered the topic of inverse functions. But what I want you to do now is, if you had me for last semester and we did this, and you remember this kind of thing, opening a window, climbing up a ladder, state the inverse action or actions, then I want you to identify yourself in your group chat. Go into your group chat and say, yes, I've had this before. Okay. And you're going to play a little bit different role with your group today, since you've had it before. All right. And the role I'm going to have you play is when I ask group questions for things, I'm going to have you kind of hold back for a little bit and see what the other responses are, and then, if you can, push people in your group for a little deeper understanding. You'll be kind of a resource person when other folks get stuck, and then you'll also kind of be pushing, well, what did you mean by that, and so on, so that you can help people get to that deeper understanding here. All right. So inverses and radical functions, and we're going to focus on the inverse functions aspect of this. All right. So inverse actions. State the inverse action or actions. So number one is opening a window. So in your group chat, type in the inverse action for opening a window. And go ahead and hit enter. And number two, state the inverse action or actions of climbing up a ladder. Write that into your group chat. And hit enter. And let me just ask group one, what do you have? What's the inverse action of opening a window?
Our inverse action was closing a window.
And climbing up a ladder, the inverse action?
Climbing down a ladder.
All right, now, if you follow an action immediately by its inverse action, what happens? What does the inverse action do to the action? And I'll open the floor up to anybody. What does it do? If you follow an action by an inverse action,
it reverses it, right?
It reverses it. So it totally cancels it out as if nothing had ever happened in the first place. Totally undoes it. It's almost like, being erased from existence, or matter and antimatter coming together and whoosh, they both disappear. Inverse action and action totally wipe each other out. All right. Now it gets a little more complicated. Do number three. State the inverse action or actions of entering a room and turning on the lights. Write that into your group chat. Okay, group four. What do you have for this? What's the inverse of this?
Turning off the lights and exiting the room.
All right, now notice what we have here. You didn't just invert each action. You also turned the order around. You said turning off lights and then exiting. How come you change the order around?
Just because logically you can't turn off the lights if you're not in the room.
That's right. If we left the room first, you can't get to the light switch probably, unless it's located super close to the door. When there are multiple actions and you have to invert, you will also have to reverse the order of the actions. All right, so the last one I'm going to do, and I'm going to put my camera on. So it says, walking into a classroom, sitting down, and opening a book. All right, so if I didn't reverse the order, this is how it would look. I would have to go like this with my book, and then exit the classroom, then stand up, and then close the book. And the problem with that is then the book has moved. I didn't totally cancel out my actions. So this one, we have to invert every action and reverse the order of everything. And when we find inverse functions, which we're going to be doing in a little bit here, we got to keep that in mind. All right, we are going to take a break now. We will start again. At 1:32 p.m. Anybody, before I take my break, anybody need to talk to me individually?
Yes.
Yes.
Oh, this is Elliot, by the way.
Hi, Elliot.
Let's see. Oh, one, thank you for sending me that Canvas link. Also,
The internship thing?
yes,
Uh-huh.
yes. Let's see, what was the question? Oh, yeah. I didn't see that there was any spot checks or anything due today from the class I missed Tuesday. Is that correct?
Let me look at our schedule.
I was just making sure my Canvas wasn't being wonky or something.
Okay, yeah, on Tuesday, we were supposed to do 5.7, but we didn't. We just finished up 5.6. So everything got delayed a day since we kind of did that. And that's why there's no specific spot check today.
Okay, gotcha. Just wanted to make sure. Thank you.
Very good. Glad you did. You're welcome. Anybody else? All right, see you in a little bit. All right, let's start up again. And, all right, we're going to go through this. Inverse statements describe verbally the inverse of the statement. So, number 1 says, add 2 to x. So, type in your answer to your group chat. What's the inverse of that statement? Go ahead and hit enter. All right, so on this one, there's 2 ways I could go about it. I could do subtract x from 2, or I could do subtract 2 from x. Okay, group 3. What did you have? Did you have either one of these? Group 3, are you there? Is Jordan there?
Yes, I had to. I spilled my Coke. I had to like turn around really quick. But yeah. So what was the question? You can ask me.
All right. Was it either one of these? Subtract 2 from x or subtract x from 2?
Subtract x from 2. The opposite of that. Add 2 to x. So I'd say 2 to x. First, I'm just taking a wild guess at it. I don't know exactly.
Okay. All right.
So 2 to x and then subtract x from 2. That would be that's what I would say. I mean, I don't know, they both look pretty similar.
All right. Let's look at them in detail then.
I messed it up.
What's happening is you're doing something to the x. All right. So when we're going to subtract, the thing that we're going to affect is that's going to go to this right here. We're not going to do this one. And then, so x is kind of the dominant factor, and something is happening to it. And same thing here, x is the dominant thing, and since we're adding to it, here we're going to subtract from it.
Okay, cool. So you're like manipulating on the variable, which is interesting.
You put the emphasis on the variable. That is correct.
Okay, that's cool, man.
Okay.
Thanks for that.
All right, so then go ahead, everybody, and do both number 2 and number 3. Type in your results for both of those. And go ahead and hit enter as soon as you're ready on either of those. I'll give you a little more time for number 3. Okay, let me go to group number 2. What did you have for number 2? Group 2.
We said divide x by 5.
And what do you have for number 3?
Add 2 to x and then divide it by 3.
Now this, what you said for number 3, is exactly the same way I would react to this, seeing this for the first time. I just negate these. But there's something wrong about this result in number 3. And does anybody see it? And you can just pop out and tell me what it is. Does anybody see the error in what we're doing in number 3?
Wouldn't you have to divide by 3 first and then add 2 to the result?
So what you're saying is, just like we had to reverse the order up here, enter a room and turn off the lights, we had to turn off the lights first and then exit the room. Same thing here. We've got to do it this. Divide the result by 3 and then add 2. So we got to reverse the order as well. And we're going to see that if you don't reverse the order as well, you won't totally undo the other thing. And what do we mean by undo? It's as if nothing has ever happened. Well, we'll show that here. Writing functions and inverses symbolically. Express the statement and its inverse symbolically. For example, divide x by 3 becomes f of x equals x divided by 3. And then the inverse. Now this, when you see -1, if you see -1, excuse me.
Bless you.
Thank you.
Bless you again.
If you see -1 as the exponent on a constant, that means this. But if you see -1 in the exponent position on a function, it does not mean this. Instead is read f inverse, the inverse function. Okay. If you wanted f of x to the -1 power, you would just have to write it like this. You're not allowed to do it like this because everybody will misinterpret it as inverse function. Okay. So if that's the regular function, then that's the inverse. And kind of like the opposite of division is multiplication, thus we have this. Alright, so now add 2 to x, you need to fill this in, f of x equals what? And then f inverse of x equals what? And then do the same thing with number 2, multiply x by 5, and then fill in the inverse over here as well. So, I'm going to give everybody a minute. When you get your answers, type them into your group chat, but don't hit enter quite yet. And go ahead and hit enter and look at other people's results. Okay, group 4, what do you have for number 1, f of x equals?
So f of x would equal x plus 2, and the inverse would be x minus 2.
Nice. And what about number 2?
we've got f of x equals 5x, and the inverse would be x divided by 5.
Okay. Those are translating worded expressions into symbols, into functions. Okay. And now everybody take some time to do number 3. Okay, and hit enter into your group chat. And group 2, what do you have for f of x? Group 2 is Aiden here? Or Annika?
Yeah, I'm here.
Okay.
For f of x, we got 3 times, wait, no. Yeah, 3 times x minus 2, sorry.
Like this?
Put the x minus 2 in parentheses.
Okay. And for f inverse?
We got x plus 2 in parentheses divided by 3.
Like that?
Yes.
Okay. And if it's a long fraction bar, the parentheses is optional. Either way would work for that. And then that's, now, subtract 2 from x becomes, alright. Now, when we had put this into words, we had said divide the result by 3 and then add 2. So let me put that down as well. Or divide by 3, do that first, and then add 2. So we have 2 possible options for the inverse. One, the first way we were writing it, add 2 to x first and then divide by 3, and the other one, divide the result by 3 and then add 2. Okay. Now, let's look at verify. Verify that the function and its inverse really do undo one another. First, we'll do this with the input of 7, and then we'll do it with an input of x. For example, verify that f of x is equal to x divided by 3. So, f inverse of x, verify that these two things are really inverse functions. The way we do it is we do like this would be the f happens first, the innermost parenthesis happens first, f of 7, and then the f inverse of that. And what's going to wind up happening when you put an inverse and an f right next to each other and you nest them parentheses wise, they should wind up killing each other off. And then you should get back to 7. And so if f was dividing by 3, then we did that first. Then if f inverse was multiplying by 3, notice these cancel out. And then you do get back to 7. It's as if this and this totally killed each other off, like climbing up a ladder and climbing down a ladder. As if nothing had ever happened to that 7 in the first place. All right. And now we did that with a specific number, 7. It turns out if you do it with a specific number 7, though, you're not sure if you really had inverse functions. Because it might have just worked with that number, but maybe there's lots of numbers that it doesn't work with. So to really know it, you have to do it with the letter x. And if you do f inverse of f of x, then you do the inner one first. F of x is x divided by 3. F inverse is 3 times that thing. The 3's cancel out, and you get to x. Aha, it's just as if these two killed each other off, and you've got to get back to x. And if it does that for the variable x, then you're 100% sure that these are inverse functions. When you do it with a single number, you think they're probably inverse functions, but maybe I just got lucky and it only works with just some numbers and not others. All right. Now, let's do it with, and so though it's a kind of a tall order here to process all these instructions. Add 2 to x, that's the function. We already did the function in the inverse. And then you're going to do this with 7, and then you're going to do it with x. So let me give you a minute to work that out. Alright, so f of x was x plus 2. The inverse was minus 2. When we do 7, you do the inner one first. Adding 2 makes that 9. F inverse of anything is you take 2 away from it. Then you're back to 7, and voila, it was as if these two killed each other out. So we're pretty confident those are inverse functions, but could have gotten lucky. Maybe it only works with some numbers. To be totally sure, we do it with x. F of x is x plus 2. F inverse of anything is that thing minus 2. And then these two kill each other off. You get back to x, voila, it's as if these killed each other off. We verified that they are, in fact, inverse functions. Okay, do it again with the multiplying by 5. I'll give you a minute, so you have to work fast to get ahead of me, and then I'm going to do it. Okay, this is 5x, x divided by 5. We just do the inner one. F of 7 is 7 times 5 is 35. F inverse of something is that thing divided by 5, which is back to 7, and yep, it's as if these things killed each other off. So let's look at this one. You do the inner one, you do this, and the outer one is dividing by 5. The 5's cancel out, you get to x, it's as if these had killed each other off. Okay. Now, we could do this also with, because we have 2 proposals for the other. Actually, let's come right up here. And I'm going to shrink my screen a little bit in this space. I can figure out which one was correct. If that's the right inverse or if this is the right inverse. With f of x, we know this is the f. Let's try it with this inverse. So let me go in black. F inverse of f of x. We do the inner one first. Now the f inverse, if I use the one that was in black, would look like this. All of this goes in for that x right there. And then I'm going to get 3x minus 4 over 3, which is not x. Doesn't seem to work. Let's try the other one. The one that we'd written in red. That's f inverse 3x minus 2. Now this one is we divide by 3. All that goes in for that x. Now the 3's cancel out. And we get x minus 2 plus 2. And then these cancel out. And we get x, and this one works. So what it tells us, that was the wrong answer. This one, when we followed the directions, divide by 3 first and then add 2, it's the only one that would check that the f inverse and the f would actually kill each other off. Alright, so give me a little feedback. Come into Discord, the main chat, and tell me if I'm going too fast, too slow, you get it, you're confused. Tell me where you're at with all this. Because we kind of had quite a bit all at once here.
I can't get into the text chat, but thank you so much for putting that down. That's awesome. Like, I had taken a synchronous variety of college algebra last time, and so I had come up with this really complex method to try to do it, and you really helped by explaining it.
Good.
So yeah, I mean, I could do it before. It would just take me like 6 years for that. So that I was turning it into a nightmare. Okay.
Alright, so what I'm seeing with feedback is generally getting it, but still a little bit of confusion and needing a bit more reinforcement, which seems understandable. Okay, this is new. Alright, inverses of simple functions. So complete this table, just use your intuition. Think, what's the opposite of that? And go as quick as you can to fill these in. So I'm going to give you a minute to do these. Okay, 30 seconds more. Get as many of these as you can, but don't think too hard. Just say, oh, I think this is the inverse function. I think that's the opposite of that. Okay, so this one is x divided by 5. This one is x minus 2. This one, the inverse of cubing is cube rooting. It's what would undo something. For instance, if you took 2 and you cube it, you would cube root that so that these would get you back to 2. Cube root of 8 is back to 2. These things totally undo each other. And there's nothing that's happening here, so there's nothing that has to happen here. And if you do f inverse of f, you get back to x again, because you're already back to x. All right, so when the function is really simple, we can find out what the inverse function is, usually very quickly, just using our intuition. But when the function is kind of complicated, like these ones here, subtract 2 from x and multiply the result by 3, and they get even a lot more complicated than that, then it's really easy to get confused finding an inverse function. And it's that point that we really need a foolproof procedure. And this is what math does. It's the strength and the challenge of math. The challenge and the strength of the math is that we just boil it down to a number of steps. You follow these steps, you always get the inverse function. The challenge to that is that we actually turn it into kind of a mindless thing. You just follow these routines and you get it. But if you do it mindlessly, most things have exceptions, and then plus you wind up really losing the idea. So the challenge in math is not to make it a mindless procedure of following the steps. So the function f of x equals 4x cubed minus 3 has 3 operations that need to happen. Suppose I told you that x was 2, and I asked you to figure out what f of x is. First thing you would do is you'd raise 2 to the 3rd power. And then you'd multiply it by 4, and then you'd subtract 3. So you do it in that order. Our foolproof procedure for generating the inverse function f inverse must do the following. It must invert each operation, like changing the multiplying by 4 to dividing by 4, the subtract 3 to add 3, so on. It must also reverse the order of the operations. So the order in which we were doing them, like the input, the first thing was raising it to the 3rd power. Well, that would wind up being the last thing when we invert it. The cube rooting should be the very last thing that we do. All right, so the claim is that the 3 steps below is a foolproof procedure and will force these 2 things, inverting each operation and reversing the order of operations, will force those 2 things above to happen. All right, and these are the 3 steps. Number 1, interchange x and y. You may first have to replace f of x, because f of x and y are the same thing. Right. Then you solve for y, and then you replace the y with f inverse of x. If we do these 3 steps, it'll always get us the inverse function. Follow these 3 steps with f of x equals 4x cubed minus 3. So I'm going to do them. I'm going to do it way over here on the side. So I replace this with y. Interchange x and y. Now when it says interchange x and y, means you write this equation down again, but every time you see a y, you put an x. Every time you see an x, you put a y. If there are multiple x's, each of them become y's and vice versa. So that's what interchanging x and y means. Then you solve for y. So how do I solve this thing for y? Now, notice, way back here, if I told you that x was 2 and I asked you to find f of 2, the very last thing you would be doing is subtracting 3. Because you'd take 2 cubed and multiply it by 4, and the last thing you would subtract 3. Now when I'm solving this equation for y, I'm going to now solve for y. And what's the first thing I got to do to solve for y? I got to do the opposite of this operation. It inverts the operation, and it's inverting the order. X. The first thing that's going to happen to the x is its 3 is going to get added to it. Okay. Now if I keep solving for y, let's notice back again. All right. If I had told you on f of x that x was 2, first thing you would do to find f of 2, you would cube it. Second thing you would do is multiply by 4. The last thing is subtract 3. All right, so we handled the subtract 3 and turn it into add 3. If we're reversing the order, the next thing should be dividing by 4. But notice, that's exactly, if I was to solve this for y, I don't take the cube root of both sides, I divide by 4. Just following the steps of solving for y forces you into the correct order. Now I'm going to turn this around. I'm going to put the y cubed over here. I'm going to put x plus 3 over 4. So you can see that the first thing that happened to x was 3 got added to it. And the next thing that happened was it was divided by 4. And then finally, to solve for y, I would cube root both sides to get rid of that cube. And then I would get y equals the cube root of x plus 3 over 4. Okay, and this is all written down over here as well. So I have just done step number 2. First step, I interchanged the x and the y. Second step, I solved for the y. But we solved for y and saw that it accomplished these two goals. It inverted each operation and it reversed the order of the operations. The last thing then is to acknowledge that this is my inverse function. So I replace the y with f inverse x. And I'm done. I have found my inverse function. So, for each of these problems, you're going to be asked to find the inverse. And let me see what, yes. And so the first one is this. F of x is equal to 2 times x minus 1 cubed. Find f inverse of x. Alright, so do the 3 steps. First thing, replace f of x with y, and then interchange x and y, and then solve for y. So I'm going to give you a minute to get going on that. I'll interrupt you before you get all the way through, but I want you to get as far as you can. So I'm going to interchange x and y. That's step one. Now I solve for y. I'll give you a tiny bit more time. Okay, I got to divide by 2. I'm going to turn it around. Then, to get y by itself, I have to get rid of the cubing first. Okay, and then, what did that give me? Well, these two things would kill each other off. Then I add 1 to both sides. Last thing, I replace y with f inverse of x. Alright, so I have found my inverse. Alright, now, similarities and differences between f and f inverse when we look at tables. Now, I'm going to take an incredibly simple function. F of x equals 3x. But this same demonstration would work no matter how complex the function was. What does this function do? It takes every input and triples it. What does the inverse function do? You can always get the inverse function from the function. All you have to do is turn around every input-output pair. This column, 3, 6, 9, goes over here. This column, 1, 2, 3, goes over here. Inverse function just turns things around on a table. That's all it does. And the inverse of making something 3 times as big is making it 3 times as small. Flips it around in the table. And it gives us some insight when we look at these steps for finding the inverse function. It's actually this first step where we interchange x and y that does all the work. When you interchange x and y, that creates the inverse function. We're just, when we do step 2 and 3, we're just changing its format so it looks like the standard way we like to write it. But you're not really changing the function at all. When you add 3 to both sides, it's not changing the function. And when you do all that stuff, the only thing that really changed the function was when you interchange the x and the y. And when you interchange the x and y in a table, you just put what's in this column, in this column, in this column, in this column. That's the inverse function. It's amazing. Now, when we look at graphs, when you take a point and you flip it around, what does it do? If you took the point 3, 1, and you turn it around so it becomes the point 1, 3, one over 3 up. Well, let's make it stand out a little more. Let's put these in red. What it does is it sends you across this. We say it reflects across the line y equal x. If I drew a line perpendicular to that dotted green line and extended it same distance over here, it would change this point into what we call its image point. If I take another point, and it's 6, 2, 4, 5, 6, 2, 6, 2, right here. Now let's flip those points around. So it's 2 over, 6 up. It does the same thing. It sends this point perpendicular to this to its image point right over here. And so what happens on an inverse function is the original function, if it had a certain shape, well, when we reflect it across this line, we'd see that same shape come over here. So they will wind up being identical images as if you folded your paper across this dotted line. The two wet ink would come off right over here and make the two graphs. Okay, so they are symmetric across the line y equals x. And one-to-one functions in the horizontal line test. So the last thing I want to mention, because we're out of time here, is, what did I just do? Okay. So if I have function like this, if I had an upward parabola and I reflected it across this, what I would get would be a sideways parabola. This point, from here to here, these points reflect to each other because they're on the line. And then this would come over like this. Now notice that the blue curve was a function. It passed the vertical line test. But the red curve is no longer a function. If this was my function f, let me get in blue. If this was my function f of x, this function over here, f inverse of x, would not be a function. It doesn't pass the vertical line test. So what we say is whenever so on the homework, you'll see problems like this. F of x equals x squared, and then they'll say x greater than or equal to 0. Now what are they doing when they do that? Then they'll ask you to find the inverse. Why are they doing this? Well, f of x equals x squared is this. If you found the inverse, it would be a sideways parabola, which wouldn't be a function. But when they say x greater than or equal to 0, they're wiping out this part. And now it passes the horizontal line test. Horizontal lines, when you reflect them across the line y equal x, become vertical lines. So if it passes the horizontal line test, we call it a one-to-one function. And then that will have a function. So this one right here, if we'd have just said, let's just have this portion of the parabola, then we would have eliminated this, and then we would have gotten this is also a function. So these restrictions will be placed so that the new function, the new inverse, will also be a function. So the homework 5.7. And we will stop here and we turn off the recording.